Greetings and welcome! Solving systems of three equations is what we're doing today. That's right, 3 variables and 3 unknowns. And technically, the skills that I teach you today could even allow you to solve a system of 5 or a system of 10. It would just take you a really long time. But we're going to focus on solving systems of 3. This is actually related to our math joke we did earlier today. You can check the video, blah, blah, blah. So the first thing I want to talk about is what would an equation with 3 variables represent? All right? Let's see. A single variable equation like x equals 2 would represent a point on a number line. All right? Like think about 2 on the number line. A 2-variable equation represents what in 2 dimensions? 2-variable equation, right? You get the coordinate plane. What would that represent?
Graph?
A graph of what? A line, right? So typical 2-variable equation represents a line. So a 3-variable equation.
Oh, is it a W or like a curve?
Well, that's actually would still be a 2-variable equation, but just with like to the 3rd power or 4th power. But think about it like this way. 1 variable was a point on a number line, right? 2-variable was a line on a coordinate plane, right? Something like this, right? But it had 2 axes. This had 1 axis. What? I don't know. Whatever. So 3 variables would actually have 3 separate dimensions we're dealing with. All right? And an equation in 3 variables would actually represent a 3-dimensional surface called a plane. All right? So P-L-A-N-E, right? So that's what a 3-variable equation would represent. Actually, and then you could actually have like this, and it's a snake on a plane. But we won't do that. So if I have 3 separate equations with 3 variables, I just want to point out that that would represent, imagine something like this. So here's 1 plane. Now when I draw like a shape like this, so imagine this in 3 dimensions, and it technically is going infinitely in all directions, okay, for a plane. All right, like a line goes infinitely in 2 directions, but it wouldn't be conducive for me to just like color the entire plane because you wouldn't be able to tell its angle or anything like that. So there's 1 plane. Here would be like another plane coming at, well actually I'll even draw it like this. And, all right, so these 2 planes, what would the intersection of those 2 planes form? That would form actually a line, is what that would form. Right, does that make sense? Think about 2 walls in this room meeting at a corner, or, well, an edge, rather, right? We have a line that is formed by them. And then if I have a 3rd plane, I'm running out of colors here. Let's say this plane goes like this, and like this, and like this, and like this. So with the purple plane, this red one intersects like that. With the blue plane, the red one intersects, wow, I'm not having a hard time visualizing. Oh, like this. All right. I almost hit it. There. So like what I have going on here, I know it's hard to see, but the intersection of all 3 planes would actually be a single point, like so. All right, does that make sense? And that would literally be like, think about the corner formed by 2 walls and the ceiling. All right. You have a single point formed at that, or the corner of a box, like a tissue box or something, right? You have a corner formed by 3 separate surfaces meeting at 1 point, okay? So here's an image. I don't expect you to draw it. This is from our text. So I don't have the rights to this image or anything, but blah, blah, blah. So there's a few different ways that you can have planes intersect. You could have them intersect kind of like at what I was just describing, where they intersect at a single point. So that's a single or a unique solution. But you could also have three planes. What happens if they all intersect at something like this, and then their solution set is infinite, where they happen to all form a line? I mean, technically, you could also have infinitely many solutions if you have like 3 sheets of paper stacked on top of each other. Those would be 3 planes that are just coincident with one another. They exist on all the same points. So there's a couple ways you could have infinitely many solutions. But then look at this no solution possibility. Right? Here's a solution between 2 planes, another solution between 2 planes, and another solution between 2 planes, but there's no commonality between those. Right? So there's no common solution between all 3. All right? Or here's 2 parallel planes, and they have 2 solutions with kind of this transversal plane, I guess I would say. But once again, those don't intersect, so there's no commonality. And then you can just have like 3 planes that never cross each other ever, like, you know, our floor and our ceiling and the ceiling of the room above us. Like, there's no intersection between those planes infinitely in all directions because they're all parallel. So graphically, that's what I'm describing. I'm not going to have you try to solve a system of 3 graphically. That would be a little bit crazy to do, by hand anyway. I mean, I'm sure if we had computer software and whatever, we'd be great at it. However, I am going to teach you how to solve a system of 3 equations algebraically. What? Algebraically, you ask? That's right. So let's write what these would look like. So I have x minus 2y plus z equals 15 is my first equation. So z's, by the way, I'll put a little slash through it to make it look different than my 2 z's. Then next equation, 2x plus 3y minus 3z equals 1. And then I'll have 4x plus 10y minus 5z equals negative 3. Okay, so think back to the problem with the mathematician on the island, right? What was the mathematician's solution? He reduced his problem to a previously solved one, right? So what I'm going to do, my method for solving a system of 3 is eliminate the same variable twice. Okay? So for instance, if I was able to eliminate this x and this x, I'd be left with, they would look different than that, but I'd be left with 2 equations, and I'd have a y and a z in each of them. So I'd have 2 equations and 2 unknowns, which is like what we did for homework last night and the night before, right? We know how to solve a system of 2. It's the system of 3 that's kind of weird to us right now. So my goal is reduce it to a previously solved problem, okay? So the way we could do that, you actually could use substitution or elimination. Maybe I'll even do both in this case. Maybe, yeah, let's try substitution first. So I use the word eliminate, but yeah, it all works out. Looking through all of these variables, 3 equations and 3 variables, there's 9 possible individual variables that I could solve for if I was solving by substitution, right? Do you remember the steps to substitution was solve one of the equations for one of its variables? That's your revised equation, and then you'd substitute it into the other one, right? Do you recall? So which of these variables is one that would be preferable to solve for by substitution? The first equation for which variable? The first equation's x would be a good choice, or the z, right? Specifically because those are weak spots. They have no coefficient besides a positive or a negative 1. All right, so let's solve the first equation for x, all right? So I'm going to solve this by substitution. So I'll have x minus 2y plus z equals 15. And what I'm going to do is move everything away from x. So I'll add 2y to both sides, and I'll subtract a z from both sides, right? Double steps right there. And I'll have x equals, and I'll write this as 2y minus z plus 15. And this is my revised equation. All right? So this is kind of like Indiana Jones and his bag of sand, except this time he had both sand and rocks, and he had to find the right combination of each. Right? So it's just a little bit more complicated. And what am I going to do with this revised equation? I'm going to plug it into the other equations, both of them, for x. And it's going to get really ugly for a minute, but it's actually going to reduce it to something that I already know how to do. So, let's see. So the first equation, if I plug in for x, I'll have 2 times, and instead of x, I'm going to write 2y minus z plus 15. And then it's, I'll stop talking for a minute so as not to confuse us. Right? So I've replaced this x entirely with this expression. Right? And now notice, even though this is really ugly looking, look at it, there's only 2 variables in it. There's only y's and z's. Right? I'm going to leave myself some room. I'm going to come back to that. I might need like a couple steps, a couple lines. And then I'm also going to plug it in for x in the other equation. So I'm going to have 4 times 2y minus z plus 15. Right? So I'm replacing x plus 10y minus 5z equals negative 3. Right? And once again, notice this is another equation written only in terms of y's and z's. And look at what I have. I happen to have a system of 2 equations and 2 unknowns, a previously solved problem. We know how to solve 2 equations and 2 unknowns. We're masters at it, right? So that's the goal. That's the mathematician putting the coconut up the second tree, or the first tree, whatever, right? That's what we just did right there. So now let's just go through and simplify this a little bit. So I'll distribute these and combine some like terms and such. Actually, that last arc is a little bit high for me because I got to try to fit possibly 2 lines of work above it. So let's see. For the first one, I'd have 4y minus 2z plus 30 plus 3y minus 3z equals 1, right? And I can go through and combine some like terms. So I've got 4y and 3y can combine. I've got 2z and, or negative 2z and negative 3z I can combine. And I might even subtract 30 from both sides. Just to, you know, whatever. So let's see, what would I get? I'd get 7y. How many z's do I have? Negative 5z equals negative 29. So there's one of my new 2 equations. I'm not done yet, though. And now for the next one, let's distribute again. So that would be 8y minus 4z plus 60, if I'm not mistaken, plus 10y minus 5z equals negative trace. And we can combine some like terms here. I've got 8y, 10y, negative 4z, negative 5z, and I'll subtract 60 from both sides, just to bring my constants all together, you know what I'm saying? So I'll have how many y? 18y's, negative 9z equals negative 63. So now notice what I've got between this guy and this guy. I've got 2 equations and 2 unknowns. And I could have given you that problem on last night's homework, and you guys would have been like, bam, I know how to do this. I'm no fool, right? You guys would have been awesome. So I've reduced it to a previously solved problem. So let's actually, looking at these 2, I'm going to rewrite the top one down here just for, you don't have to rewrite it as many times as I am. I'm just kind of, for the sake of visual spacing, because there's a lot of numbers floating around. So here's my system, right? Bam. We already know how to do this. Make that engineer climb back up that tree, right? So, what method would you want to use to solve this? Substitution or elimination? Elimination, I think I agree. And what would the quote-unquote LCD between 18 and 7 be? Let's see, 18 is composed of what, 9 and 2 and 7? I think I just have to straight up multiply those. So that'd be what, 70 plus 56, what's that, 136 or something? Did I do that right? 126. That's big, but whatever. And how about between 9 and 5? 45. I think I like 45 better. I'm not even 100% sure 126 is right. Well, actually, I kind of am, but whatever. All right, so what do I multiply the top equation by? 5. And what do I multiply the bottom equation by? 9. And one of those you have to make negative. Sure, we'll make the bottom one not negative. It doesn't technically matter. Okay, I'm going to end up writing my next work kind of just over here just to give us some room. So 5 times 18, 50 plus 40 is 90y minus 45z equals, let's see, 5 times 15 plus 300, negative 315. Is that right? I think so. Next one, negative 9 times 7, negative 63y plus 45z equals, ooh, man, what's a good way we could do that one? It's going to be positive. We could do 10 times 29 is 290, and then what would I have to do? Subtract a 29 from it, right? 290 minus 29. Do you guys know what I'm doing as my scratch work here? Let me write out what I'm doing. I'm saying that 9 times 29 is the same as basically 10 minus 1 times 29 is what I'm doing. 29 times 10 is 290. 29 times negative 1 is negative 29. See what I'm doing there? And then 290 minus 29 is kind of like 290 minus 30, right? So that's 260, and I have to, what, add 1 to that, so 261. Right? You like my little scratch work there? Right? I mean, if I was trapped on a desert island without a calculator, that's how I would have done that math. Okay. Did I accomplish my goal? What was my goal? Yeah, I've got, hey, bam, I've got 2 opposite variables. That's exactly what I wanted. Add them up. Let's see, so I've got 90 minus 63. Is that 27y? Am I not mistaken? The z's cancel out like I wanted. Let's see, what's that? What's that, 29? No, 39 plus 15. And it will be negative 39 plus 15. Oh, what am I doing? 54, negative 54. Bam, sorry. I heard you say something. I didn't process it though, my bad. And now, oh, hey, guys, look at what we got. We've got a system of 1 equation and 1 variable. You know how to solve that, right? You probably never thought about it as a system, but how would you solve for y here? Sure, divide both sides by 27. We get y equals negative 2. Hey, oh, so we're done now, right? Whew. Oh, what do you mean? What do we have to find? Oh man, we gotta find 2 more variables. Yikes. So I found 1. Wow, this problem is getting beastly. Where should I plug this in to find another variable? Oh, plug it in this one? Is this what you're looking at? As a matter of fact, I'd have to plug it into either of these 2 or, yeah, either of those 2, really. Or, I mean, technically you could plug it into either of those if you want, but those will all have bigger numbers. What I don't want to do, I wouldn't want to plug it into one of these 3. Why wouldn't I want to do that? Yeah, because, right, if I plug in y here, I still would have an unknown. I have 2 unknowns. I'd rather plug it in something where I know I'm going to get another answer. So I think I actually like this option the best. Those seem like the smallest numbers that I have available to me, right? So I just want to kind of walk you guys through that logic, the thought process as to why we chose that. Actually, I might even fit that work right in over here a little bit. So let's see, 7 times negative 2 minus 5z equals negative 29. You could keep working vertically down if you want, because I realized that this math problem, look at like just, it's like a lot of math there. Bam, math. So the spatial arrangement of this to have your work make any sense could be helpful, but 7 times negative 2 is negative 14. Okay, bam, there we go. Minus 5z equals negative 29. And hey, this is a one variable equation now. I know how to do this. Add 14, add 14. This looks friendly. Negative 5z equals, what's that, negative 15? Divide, divide. And I get z equals 3. So now I just need one more. What could I do to find an x? Plug it in one of the original 3, or, oh, this one looks actually really good right there. It's already solved for an x, you know. Let's see, I'm going to actually draw a different colored arrow. We'll use purple arrows this time. Let's see, can I even fit it all in one? So I'm going to go, and I'll go like this with the z combining with it. And these are both plugging in for the y and the z. You like that? Man, this is beautiful with all of these colors here. I need to like print this out as a wallpaper for my house. So let's see. Man, I've got to keep like scrolling back and forth. So x equals 2y minus z plus 15. So let's write this down. So x equals 2. Instead of y, it's negative 2. And then what was it? Minus z, was it? So minus 3 plus 15. Let me just verify. Yep. And hey, I could solve this. Negative 4 minus 3 plus 15. Negative 7 plus 15. And I get x equals positive 8. So you could write your solution as just those 3 kind of combined. You could also write it, watch this, bam, bam, bam. That's an ordered triple. That's right, ordered triple. How do you like that? Right? As opposed to an ordered pair, right? You know what I'm saying? So, wow, that is wicked cool, huh? Wicked cool. So I just want to point out what we did as our approach was this one concept, right? Like the mathematician climbing up the tree to get the coconut and putting it into the first tree to get the engineer to pull it down, right? We broke this down into a problem we already knew how to solve. All right, this is something that mathematicians like to do, and it makes bigger problems easier. We break it down, right? So I happen to use substitution approach is what I did for my first kind of approach here, right? This was all substitution, right? What I was doing. But I want to point out that you could also have done elimination method. Let me actually find, that one actually would have been nice for elimination. Here, let's do one for elimination. And actually, I think I might not even be able to fit it all on this side. Wow, that one problem was just massive. I kind of like that picture right there still. So let's try one more. I might not take it the whole way. I think we'll just do, the first portion where I break it down into, a system of 2. So let's say I had this. What if I have 5x minus 2y plus z equals 11? Let's say I have 2x plus y plus 3z equals 0, right? Sure. And let's say I have 6x minus 2y minus 2z equals 16. Bam. System of 3. Okay, I'll let you guys finish writing. So, if I was to solve this by substitution, what would my targets be? Right? Bam, perfect. Okay? You guys agree? So you could solve for this y and then take your revised equation and plug it into both of those other two, eliminating both of the y's in both of the equations, right? So it kills the same variable twice. And by doing so, you're left with two equations and two variables, right? So we could have done that. We're going to use elimination tactics. So between these, what would the quote-unquote LCD between 5, 2, and 6 be? 30, okay. How about between 2, 1, and 2? That one's my fan favorite right there. And between 1, 3, and 2? 6. So I think we know what ones we want to get opposite coefficients for, right? Probably shoot for the middle one, the y's there. And actually, I'm going to label my equations just to kind of make things a little easier. Sometimes they'll be labeled with capital letters. We could label them 1, 2, 3. I think I use numbers, but I'll just put 1 in a circle, 2 in a circle, 3 in a circle, just for sake of ease of communication. It kind of just organizes our work a little bit. All right. Now, yeah, I think typically they use letters, but whatever. We're fine. We're fine. As long as you have some way to indicate. So if I want opposite coefficients for the y's, what do I have to multiply equation 1 by? Well, it's already got the 2 portion.
But then sometimes 3, you can't multiply this one of them by because we have an actual, because there's 3 of them, so if it was just 2, you'd multiply 1 by negative 1 multiplied by 3, positive 2, negative 2,
Right. So the point that she's making is that for my quote-unquote opposite variables, I only want one of the equations to end up being opposite of the other 2. Okay? Right? Because I can't have 3 things that are opposite of each other. That doesn't make sense. Right? So I'm actually, what I'm going to shoot for is I'll keep this one -2, this one -2, and I'll make this one +2. And the +2 will be the opposite of those ones. Does that make sense?
But shouldn't it be positive 4? Is it going to add them?
Nope. I'm going to add them separately is what I'll end up doing. Yeah, I see what you're asking. You were thinking if I make this 4 to eliminate with both of those, I'm going to do 2 separate eliminations is what I'll end up doing. But I do see the confusion. So I'm going to keep equation 1 the same. I'm going to keep equation 3 the same. And what should I multiply equation 2 by? 2. So I'm going to write this down. Watch this. I'm going to write 2 times equation 2. Oh, wow, that's a Waldo right there. Loop-de-2. Right? So let's see. 2 times 2x is 4x. 2 times 1y is plus 2y. And 2 times 3z is plus 6z. And 2 times 0 is 0. All right? And I think you guys agree that this is the opposite of these 2. So the next thing I'm going to do is I'm going to add this with equation 1, and I'm going to add this with equation 3. And watch how I'd write that out. So I'm going to actually write, yeah, that's fine. So 2 times 2 plus 1. And then I'm also going to do 2 times 2 plus 3. So see, I'm just kind of using this to label where these things are coming from. Because it's easy if you just have line, line, line. It's like, how are these even related to each other, right? So I'm just trying to have kind of like a nice little format to track what all my work is. You could even like kind of almost keep like a little margin that you just have that all labeled in if you wanted. Let's see. So let's add this with equation 1. 4x plus 5x is 9x. Goodness, that's a pretty good sneeze. 2y and negative 2y is 0y. Hooray! And 6z plus 1z is plus 7z equals, and 11 plus 0 is 11. Okay? And then I've got 2 times equation 2 plus 3. So I'm doing this guy plus this guy. All right, so 4x and 6x is 10x. Positive 2y and negative 2y is 0y's, which is what I wanted. I wanted to eliminate that variable. And then I've got, see, now I already got lost just looking back and forth. What was I doing? Oh, I'm adding this one and equation 3. Aha, it's labeled. Perfect. So negative 2z plus 6z is 4z. I almost wrote 8z there for a moment. And then 16 and 0 is 16. And look, lo and behold, I've got a system of 2 equations and 2 variables because I killed the same variable twice. All right? This wouldn't have helped if I eliminated an x one time and a y the other time, because I'd have 2 equations with 2 different types of variables in each of them. So that wouldn't have been as productive for me, right? And then we could solve from here. And sometimes what you'll do is actually relabel these. I could, for instance, label this now equation 4 and this equation 5 or something if I wanted to continue using elimination to solve this. But if you ended up liking using, you know, if one of these ended up being a substitution-worthy method, that's fine. You don't have to commit to elimination through the whole process. You could do elimination once and then substitution and mix it all up, whatever is convenient. So let's see, if this is 4 and 5, I'm not going to go the whole way, but I'm going to use elimination on this. What would the LCD for the x's have been? 90, I believe, yeah. And for the z's, it would be 28. So we're not going to do this, but what would I multiply equation 4 by to get opposite coefficients? So I would do 4 times equation 4. I'm not even going to write it out. And what would I multiply equation 5 by? Would that give me opposite coefficients, though? Yeah, one of those would have to be negative, right? And then I'd end up being able to eliminate the z's next, and I'd go from there, right? So, so that's the idea. I'm not going to do that because, hey, we'll make that engineer climb up that tree. So that is the big idea, and I think you can see how this structure could then also be used for a system of 4 and 4 variables, right? Where you could eliminate the same variable 3 times, it'd boil it down to a system of 3. Then you'd eliminate the same variable 2 times, and that'd boil it down to a system of 2. You'd eliminate the same variable 1 time, and that'd boil it down to a system of 1, and then you'd be able to work your way back and do the whole thing. So one of the things I'd like to point out is that these problems end up being very long, right, if you look at our first example. So a single mistake can poison the whole thing, right? So I recommend that while you're checking your answers, the moment you find your first answer, check it. Like, don't try to like keep going with a wrong answer, because it will just make all of your work wrong. Okay, so so do that for sure. All right, everybody, have a good day. Bye.